Good morning, good afternoon, good evening. My name is Tim Cho, and maybe unlike a lot of your speakers, I don't have an MD, I don't have an MPH, but I do have a PhD in electrical engineering. And over the past many years, I've spent a lot of time in the world of commercial computing. I served as the first president of Oracle's cloud computing business, and actually about 15 years ago, returned back to Stanford and started the first class on cloud computing. So I really appreciate the AHA inviting me to speak to you today. And what I want to talk about is really three essential things. One, a challenge I learned from a student of mine in my cloud computing class that led to a new technology we refer to as an edge cloud. And I want to show you how that technology could break through three essential challenges in developing AI for rare diseases. So with that, let me start the screen up, share screen, here we go. Well, if you can see my cat, that's Kate. And I'm gonna go to present. Here we go. So I slightly changed the title. I know it said big data for small problems, and I changed it to big data for small people. You'll see in a minute. But I think what I'm going to share with you will apply to how do we crack the problem of developing AI for rare diseases. So as I told you right at the beginning, I have spent a long career in the world of commercial computing, startup class in cloud computing at Stanford. And about 6 years ago, a student arrives who some of you may know, Dr. Anthony Chang, who introduces me to the world of pediatric medicine and the challenges that they face. And it was quite remarkable to me. This actually is a situation that happened early last year. A boy in Southern California went undiagnosed with brain cancer for well over a month because it was too difficult to share data between two hospitals and one clinic. People are still using CD-ROMs to exchange images, which is totally stunning in the modern era. Anthony also told me a story of a kid he was providing consulting services for in Myanmar. They wanted to share with him the echo. They could not get it to him in time. She died on the operating room table. And unfortunately, he got to see it later and said, oh, I could have explained exactly what they needed to do. If you look at the challenge of healthcare globally, one of my old friends is Carolyn Miles, who just retired as CEO of Save the Children. She's very aware of the project that we've embarked on. And she said, well, you know, the #1 killer of kids in Africa is pneumonia. And that's not because there's not low-cost scanner technology. There's just no one to read the scan, which obviously brings us to the world of AI. And how can AI take the brains of the smartest pediatric cardiologists in Orange County and move them around the world? Well, I think many of you already are aware of this. This is a conference that got run last year at Texas Children's. The big challenge is there's not enough data. There's not enough data, and amusingly enough here, not enough ultrasound data. And I think those of you who are aware of the work in artificial intelligence do know that there's a central idea here, which is with neural networks, if we can bring more data to the problem and more compute, we can deliver higher and higher degrees of accuracy. So the challenge of how do we get more data is clear to everyone. And the implications of not having that data is that, yeah, we might be able to build a deep learning application, but it's going to be very brittle. Obviously, building a pneumonia diagnostic for kids in Africa with data from kids in Palo Alto is never going to work. So when we look at the challenge here, what's the root cause of this? And I want to make something very clear to you. I do not believe the data to drive AI is sitting in the EMR or the EHR. These are just giant billing systems, right? So where is the data? Well, the data is in the healthcare machines. And when I say healthcare machine, I mean ultrasound, MRI scanner, CT, blood glucose monitors, gene sequencers, et cetera. It's sitting in those healthcare machines. But because those machines are not connected, live in little silos, it just becomes digital exhaust. The Echo lab at Stanford Children's generates 50 gig of data per day. All of that data is just going into the air. So we launched a project a little bit over a year ago, a bunch of guys who are all and women in the world of infrastructure. We launched a project to enable safe, secure, precise data sharing from all million healthcare machines in all 500 children's hospitals in the world. And that technology that we have developed, we refer to as an edge cloud. So I'm going to take a few minutes and give you a brief introduction to what this technology enables. So the edge cloud first is, if you're familiar with center cloud computing, it contains edge compute and storage services, a relatively powerful computer and storage that is at the edge in the building. You'll see a picture of it later. The edge compute and storage is connected with edge networking services. This is both to connect server to server or compute to compute within the zone, as well as across zones and from the zone, from the hospital, from the building to the external world. We have designed everything around a cellular first strategy, a wireless first strategy, and actually have demonstrated the power of using 5G technology for implementing the edge networking services. Edge networking services then, and the compute and storage, enable the creation of digital twin applications. So the digital twin application is a specific kind of edge application. It is designed to replicate all of the data. When I say all the data, I am saying the static data, the environmental data, where's the machine located, the dynamic data, what was the last error log, as well as what is the gnomic data, the gene sequence, the blood analysis, the ultrasound, et cetera. The digital twin application then provides that data in an authorized mechanism to edge data services. So edge data services then will, with permissions, provide that data to edge cloud applications. This is extremely fine grained. It's down to one machine and one application. You can choose to share that data. So those edge cloud applications are developed using the Bevel Cloud Studio. For those of you who are interested, please reach out. I'll show you later contact information. We just had our first conference. We called it Invent 21, and we showed 6 different applications that were developed with the Bevel Cloud Studio. So how does this all address the challenges of applying AI to rare diseases? And I'm going to say to you, there are 3 big challenges here. The first challenge is, and we talked about this, is so how do you get large, diverse data sets for rare diseases? I mean, no one hospital, children's or adult, is going to see enough data. So how do you acquire large data sets, diverse data sets for training AI algorithms? Well, I just explained it. Let's get it from the machine itself, from any healthcare machine in the world. And just to be clear, once a digital twin application exists, the data coming out of that is standardized. So I don't care if that machine is in Rwanda, rural California, or Beijing, it's the same data that's coming out that the edge applications can then access with authorization. So number 1, how do you acquire it? Okay. Number 2, and we all know this, how do you train these algorithms while preserving privacy? And I'm going to show you 2 mechanisms that we have developed in order to do this. The first is, well, okay, let's go de-identify the data. And actually, we're partnered with a company called Glendor, who has developed a technology to de-identify, and right now I'm talking about images, but de-identify the data out of the images themselves, which, as many of you know, there's burned in data there, as well as out of the metadata. So number one, I can get rid of de-identify all the data out of the images at the edge, on the third floor of the building before it's transferred to any center cloud, Azure, GCP, et cetera. The other alternative I have is I can use federated learning. Some of you may be aware of this technology. It's basically a technology that was developed on the consumer side. So just to use it as an example, Siri. So Siri is not taking every one of your voice prints and sending it to the Apple cloud for Apple to analyze, train on, et cetera. Number one, because privacy preservation, and number two, network preservation. They don't want to spend all the time, energy, money to transmit all that data. And the other point I want to make with you is it allows them to learn continuously. I think the world we've come from is, oh, I'm going to batch up all the images, all the voice prints, et cetera, and then I'm going to learn in batch mode and then take that inference engine and deploy a very kind of, we'll call it old school way of thinking about the world. All of you are medical doctors. We don't learn in a batch mode. We learn continuously. So why not apply the same techniques that are being used at Siri and Alexa for network and privacy preservation and apply them to the world of healthcare? And we're actually working with USC and a team they have called FedML to bring FedML to the edge so that you can learn continuously on data coming off of these healthcare machines. And last, and I mentioned it, hey, you come up with a great inference engine to do pneumonia diagnostics. How do you deploy it at the point of care? And I said earlier on, I'll show you a picture of an edge server. So there's an edge server. It's not much bigger than your hand. So it's simple to deploy on a global basis to the point of care anywhere on the planet. So in summary, AI for thousands of rare diseases from A through Z. You're going to need to get data, and data from any machine is now accessible safely and precisely. Number two, if you're going to solve AI for thousands of rare diseases, you're going to have to protect privacy. I just went through 2 ways that you could do that and learn continuously. And finally, for thousands of these rare diseases from A through Z, once you figure this out, once that inferencing engine is running, you can now deploy this on a global basis. So I hope you'll join us on this mission that we've had to fundamentally transform children's healthcare for rare diseases or for not so rare diseases. That's a LinkedIn address for me. Glad for you to connect. moonshot@bevelcloud.io will give you access to the Bevel Cloud Studio. And I'm glad to talk to any of you more about the work that we have been doing. Again, thanks to the American Heart Association for giving me the time. And I hope all of you learned something from this and will take the next step to fundamentally transforming healthcare on the planet.